Okay. So far we have studied the Newtonian relativity, as you know. Okay. And in this Newtonian relativity is based on Galilean relativity, Galilean transformations. I hope my voice is clear, right?
Yes, sir, but are you presenting something because nothing is visible?
Wait a second. Let us forward, I suppose. Okay. Yeah. The screen is visible, I guess. Yeah.
Yes, sir.
Okay. So till now we have studied the Newtonian relativity, which is based on the Galilean transformations. Okay. And the Galilean transformations, coordinate transformations are like this. Okay. When the motion of S prime frame is in x direction. There are two frames, S and S prime frames. S prime frame moving in the x direction. Okay. Take this y-axis also. Okay. And of course, to remove the confusion, okay, you can equivalently be in this S prime frame, make this S prime frame as stationary and move this S frame in the opposite direction. But our convention to remove the confusion will always be like, consider the S prime as moving frame, okay, moving frame, and S as stationary frame, always. This this will should be the convention. Okay. If you do the opposite thing, you just will get your GT as IGT and IGT as GT. It's where GT denotes Galilean transformation and IGT denotes inverse Galilean transformations. This will transform when you will consider the S prime as stationary, okay, and S as moving. But by convention, you follow this rule, and this will not happen. You just only need to consider one thing, that these transformation will always represent your Galilean transformations, and the opposite way will be the inverse Galilean transformations. Okay, so what we studied till now is that relativity is just the framework where we translate our physics from one frame to other, or say we observe things from one frame and another frame and try to relate our observations from these coordinate transformations. Okay, so now we'll proceed further and see. Also, we have also uh, looked at Maxwell's equations. Okay, there were four Maxwell's equations, and those were, anyone remember? This was Gauss law for, uh, okay, consider the vacuum case. Okay, I'm just considering the vacuum case. And this is my, another one is curl. The above two equations are divergence, and this is of curl, okay, and the curl of B. It's electric field, the change in electric field. Okay, so what does this tell? That the divergence of the electric field and magnetic fields are zero, In the vacuum means there is no charge density, no charge present, no sources of charge, no sources of electric field. Okay, this is electric, and this implies there, of course, there this will always be valid and always be zero. Means there exist no monopoles, magnetic monopoles, but of course the electric monopoles can exist. And of course in the vacuum case, our current density vector will be zero in the vacuum case. And using these equations we found some equations that are electromagnetic wave equations. Wave equations. What were they? Anyone remembers? Suppose it's simple wave equation. Suppose I am taking the 1D case. Our usual, uh, suppose I am taking for electric field. That's our usual one. This is permeability. This is permittivity. Okay, and this will be with respect to x square. Okay, in x direction, and similarly for B field. Both of these fields travel with a unique speed, that is c is equals to 1 by mu naught, and it is a constant. Okay, 2.99 something into 10 to the power 8 meter per second. Okay, but there is an issue. The issue was the issue was that under Galilean transformations, okay, the Maxwell's equation, and secondly the electromagnetic wave equations are not invariant. They are not invariant. What does this imply? That this implies that there must exist some spatial rest frame, okay, where these equations will be valid. Okay, there must exist some spatial rest frame where these equations will be valid. Otherwise, they will transform. They will transform non-trivially. Okay. I have given you one question in the last class also. So that to transform the wave equation, general wave equation under the Galilean transformations, and I told you that it will not be invariant. Okay, if you have done that, then you must realize that these wave equations for electromagnetic wave will also transform non-trivially and will not be invariant in regard with different frames of reference or for different observers moving with constant speeds, or say the inertial frames. Okay, so initially people considered historically people got an idea that if every if every wave do require a medium for its propagation for its propagation, then the light should also must have also a medium to propagate through. Okay, and they called it lumino luminiferous ether. Okay, the scientific word is ether, not aether, but people sometimes call it ether as a uh, uh, another component of the universe historically. But in science, we do usually call it ether. Okay, let me write it neatly. Okay, and then people tried to see, like Michelson and Morley, tried to test the ether wind and they tried to calculate the velocity of this ether wind if it is dynamical or not dynamical. Okay, I will explain you now things better. Wait. Okay, in the late 19th century, after calculations of Maxwell's that we did, that electromagnetic waves are actually a disturbance in so-called this luminiferous ether, okay, medium, and the c as the speed of light in that particular is the speed with respect, they consider this is the speed with respect to that ether free. They considered that because this particular equation is only valid for a particular rest frame. Okay, they considered that the resulting speed will be with respect to that ether frame and which should be at rest according to them. Okay, and these ether defines a perfect rest frame. This defines a perfect rest frame. Okay, now if ether is just like other mediums and it can be dynamical or moving, but we will say uh, not dynamical. Okay, maybe it is dynamical, even if it is dynamical with something else, but they considered that if the speed is traveling, okay, with respect to ether, this speed has a particular speed that is c with respect to this ether, no matter this ether is dynamical or what. Okay, with respect to this ether, this propagation of waves, electromagnetic waves, have the speed that is constant, that is c. But according to the Galilean transformations, we have seen that if something is moving with respect to it, suppose something is moving with respect to it, okay, this is my s prime frame and the ether is suppose s frame. So what will be the uh, speed of light in s prime frame? It will be c minus v, of course, right? According to Galilean transformation, the speed of light should change. So let's draw it neatly and try to see what was what was actually the Michelson Morley experiment. Okay, and this diagram you can see like this. No, this is not of any experiment diagram, but this is just intuition based diagram. The space is filled with ether. Okay, the space is filled with ether, and this is my light propagating. Okay, with this respect to this ether, okay, consider the ether as my S frame. Okay, and with respect to this ether, okay, I have my earth. Okay, this is my earth. Consider my Earth is moving with some velocity in some direction, random direction, and this Earth is denoted, Earth frame can be denoted by S prime frame because it is moving. Okay, so with respect to this is my Earth. Okay, the velocity with respect to Earth, and this is the velocity of Earth, of course, and this is the velocity with respect to ether. Okay, like this. Now let's start the main Michelson-Morley experiment. Okay, okay. So it was done around. So firstly, Michelson uh, alone did this. I think thought of this kind of an experiment in 1881, but then Michelson Morley, Morley joined him later on in this experiment. Okay, that's why it is called Michelson-Morley experiment. And the idea was that use wave nature of light, use wave nature of light, okay, to build an an interferometer, interferometer. Okay, so the idea they want to test uh, was of ether, and they want to actually calculate the velocity of ether wind. Okay, you see here in the above, this is the original setup of the Michelson-Morley interferometer. Okay, it is mounted or it is mounted on a stone slab. This is the stone slab here, this one. Okay, and it is floating on an annular trough of mercury. It is called some channel or something. Okay, in this there is mercury in liquid form, and it is floating over it to reduce the friction while rotation. This interferometer do rotate, can rotate. Okay, and to reduce the friction, uh, like it should be like negligible while rotation. So they used mercury for it. Okay, this is the thing, and they actually wanted to calculate the ether wind, velocity of ether wind, or the existence of ether actually. Usually, I mean, previously people have tried to calculate the existence of ether, like in Fizeau experiment. Fizeau, let it quickly. Yeah, it was regular experiment, uh, but it was not about ether experiment. It was about uh, like when light is traveling through a moving medium of water, how this affects the speed of light. The question was, do this moving medium drags the light, and the result was yes, but partially, but partially, it drags partially, and the speed was something like uh, it's personal. Okay, the speed would be like this, plus minus b 1 minus m squared. Okay, well, see the speed of light, of course, speed of light, and v is speed of water medium. Okay, and n is refractive index. Okay, this was like basic experiment uh, performed by Fizu. Okay, in 18. But similar to this experiment, we now want to see what if the light, uh, we want to check if the light is dragged by ether or not. Okay, so suppose if you are in a still medium, okay, if you are in a still water, the water is still, it's not moving, but your but your object is moving. Okay, so it will feel when you will be in this frame, the moving frame, for you this moving frame will be actually at rest, and you will feel a wind of water or some flow of water towards you. It's similar to like if it's raining, and you start to run, and you start to run. Okay, then you will feel the this rain towards you. And the similar thing will happen here. Suppose there is an ether filling the all of the universe, okay, and if it is at rest, suppose with respect to light frame, okay, so this Earth, suppose there is a Earth, okay, and it is moving in this ether frame with some velocity, then it will, you can see, for this earth frame, when when you will see, suppose this, when you will consider the earth as your stationary frame, you will equivalently say that the ether is coming towards you call it ether wind. Okay, so for us, we the earth is at rest, so we will experience this ether as ether wind equivalently. Okay, so let's now do some calculation thing. Okay, so this was the diagram for it. Our Earth is doing an orbital motion around Sun, and this motion, due to this motion of Earth, you will feel some kind of ether wind. Okay, any questions till now? Okay, so uh, let me. This is some mirror. Okay, this is another mirror, and there is a light source. Okay, so let me draw something straight. So, So one more thing, I need to have this thing. Okay, this is light source. This is my mirror 2, suppose. This is my mirror 1. Okay, now what happens? The light here enters this crystal, okay, and gets partially reflected and partially transmitted, okay, and this light comes here from here, goes halfway here and halfway here, okay. This light, after reflection, complete reflection, comes back, and after complete reflection comes back, and then these waves, these two waves, suppose this is my arm 1 of length 2, this is arm 1, uh, another arm of length 1, okay, with respect to mirror 1, and here I have some kind of detector, okay, detector, okay. Then these both waves again recombine and received at detector, okay. This is the basic figure or diagram, basic apparatus of Michelson Morley experiment. Okay, let's do the calculation first. Now, now yeah, this is, you can name it beam splitter. Beam splitter, and it is some kind of like a a piece of silver glass, okay, which reflects half of light and transmits half of light, half of it. Okay. Now, what happens when they recombine depends on the optical phase difference, the experience along the two paths. What happens when they recombine depends on the optical path difference. This is interferometer, of course, so there will be some phenomena of interference here. Optical path difference. Okay. The experience, who, the light in different arms. The experience, okay, along two paths, 1 and 2, or say L1 and L2. Okay. Now let's define something. Okay. Suppose T1 is the time taken to transverse path L1. Okay. And T2 is the time taken to transverse path L2. Okay. And define this delta T as the difference T2 minus T1. Okay. And C delta T, we will call it the optical path difference. Okay, this is simple to calculate. We will calculate it faster. And what does this actually measures? What does this actually measures? This measures. You can guess it. What does it measure? It's simple. You understand, no? What is T1? It is like when light goes from this right hand side and get reflected back and comes here, and this is the path traversed by the light, and the time taken by it will be T1, and the in this arm L2 the time taken will be T2, and the difference between both will be the optical path difference, because there will be some path difference in experienced by the light while traveling these two paths. Okay, and we define that path difference by this quantity. Okay, so this measures the difference in distance traversed, traversed by light as it back and forth through two arms. Okay, that's it. You understand this. Now let's see uh, another thing, that is phase difference. Okay, phase difference is defined like this. Okay, by lambda, it gives the phase difference. Okay, optical phase difference. Okay, since light is a wave, okay, it is an important it is an important quantity to know what happens when light recombines. Okay, fine. So if suppose if this phase this phase is like in integer forms, okay, this means the light the two lights, two incoming waves do interfere. How do they interfere in this form? Tell me, you have studied in your previous classes, constructively or destructively? Hmm? Arpit, Trisha, how do two waves interfere if the phase difference is this? Do anybody know? You have studied in your 11th or 12th class, I guess. How do they interfere? Constructively or destructively? There is another case. Just tell me. If you don't remember, also, just tell me if I don't remember.
So the first one should be constructively and the second one should be destructively.
Yes, so it should be constructively. They interfere constructively and they interfere destructively. Okay, so you also define like part difference, right? Again, so it should be n lambda of like integer multiples of lambda. So this is what we have defined, right? This is the optical part difference, which is this one, and it should be, if it is n lambda integer multiples of lambda, then it should interfere constructively. And if it is not integer, if it is fractional like this, it will interfere destructively. Okay, so we can just see like this. When you combine both, okay, their like difference is just zero. Okay, so they will combine constructively like this. Their amplitude will be added up, and if they combine like this, just as an opposite phase, okay, so this will be flat line, right? This will be a flat line because all of its points are just opposite. So now we expect, what do we expect? That this delta t by lambda be some value between n lambda, or say this is phase difference, so I should not write the this. So n n plus by 2. Okay, we expect that this phase difference should be any value between the n and the n plus 1. Okay, so the recombined amplitude, okay, should be between perfect constructive interference, that is a bright fringe. There we will see a bright fringe. Okay, and perfect, perfectly constructive, perfectly destructive. There we will see a dark fringe. There we will see a dark fringe. So because in this experiment, why? Because in this experiment we have used white light. Why? What is the need of white light? What is the importance of white light? Why are we using white light in this experiment? Why not any monochromatic light? What is the specialty, or what is the difference between monochromatic and white light? What does it allow? It gives us a wide range, gives us a wide range of wavelengths, because you can have all wavelength. of electromagnetic spectrum. Okay, so we will expect that we will surely see an interference pattern in the detector on screen, on detector screen. Okay. Means for of course for some lambda we will see some constructive interference because we have all values of lambda now. For some lambda we will see some destructive interference, and similar to this fringe they have observed actually. Okay, this is the fringe Michelson mold experiment. Michelson and Morley have seen these kind of fringes. These are constructive and destructive ones. Okay, these are destructive ones. These are constructive, and you see the different colors because of all values of lambda is considered. We are considered here. So it's just a mixture. So now our goal is to calculate the optical phase difference, but let's do a simple. Uh, what is the time now? Okay, I will take just few more minutes and we will complete this. Okay, so we have a frame again. I should draw it. Okay, this is my ether frame. This is my ether S frame. Okay, this is my earth in the ether. Okay, suppose I have my setup here. Okay, this is M2, L2, this is L1, M1. Okay, and this is earth frame. This is earth frame, and which is S prime because it is moving in this ether. Okay, this is my ether. It is at rest. In the ether frame, the speed of light is at rest. So consider a case. Okay, suppose my Earth's velocity is v. So my v is parallel to suppose arm 1. Okay, suppose my velocity is parallel to this arm 1, this length 1. So what will be the time taken by the light? Can you now tell me what will be the time taken by the light in traversing this L1 distance and coming back? What should be the time taken? Arpit, what should be the time taken?
So 2L1 by V.
Arpit is not here today. Okay, fine. So, what should be the time, Trisha?
2L1 by V.
L1 by,
So twice of L1 because you said it will like travel back as well, right?
but you are living on thing because this frame is moving with speed v. I am I mean the time taken by the light, and light is moving with the speed c, but the Earth is also moving with speed v. So what should be the time taken by the light in this frame, Earth frame? Is it, or will this be like this? What will happen in this frame? So you see, our Earth is moving in this direction. So if the light is moving in this direction, suppose, so what will happen? What will happen?
Should add
According
up.
to, yeah, they will add up. Of course, they will add up. And suppose if the light is coming back, what will happen? Right? It will be decreased. You can see this from Galilean transformation also. Okay, if the light is going in this direction and this V is also in this direction, okay, so what will happen? According to Galilean transformation, uh, actually they will decrease. Okay, because in this frame, S prime frame, it will be decreased in S prime frame. They will add up in the S frame. They will add up in the S frame, and this will be in the S frame. But in S prime frame, they will decrease. Of course, you can see this right from train experiment also. When we were considering the train, okay, in S prime frame, okay, so if someone is like running here with some, if this is moving here with velocity v, and it is the person is running with velocity u in S prime frame, uh, or say this is my ground person, it is at rest. Okay, so in S frame, my velocity, he will see this man is running with u plus v, is running with u plus v in S frame. Okay, so similarly in S frame we will see this light is moving with c plus v, and in the backward direction it is moving with c minus v. But in the S prime frame, this is in S prime frame, you will calculate the velocity, you will get that c1 c minus v is my velocity when they are in same direction. Okay, but when they are in opposite direction, we will get like this kind of thing. Let me write it again. Okay, now velocity, I mean with direction, if you are taking, it will be minus c in, like, suppose this is minus x direction if I am taking this vector. Okay, and this will be of course in, sorry, I'm missing something. Plus connection. It should be c plus 1, but how? The c plus v, help me now. When they are moving in opposite direction, my earth is moving in this direction, and the speed, the light is moving in opposite direction. How will this be c plus v? Like this they add up. Tell me. Actually my c will be minus c. Okay, in this direction, in this regard, and this will remain as the this is this, and you just take it, it will be c plus v, but it just tells you the direction, I suppose. Hmm. Okay, let's go with the intuition then. I will get back to it. Let's go with the intuition. So basically, in S prime frame, one will traverse take time this plus also take time this, because they are moving in one direction and the opposite direction. And what will be the time 2 now? What will be the time 2 in like traversing the distance of L2? So actually, since the earth is moving, okay, so my beam splitter will also move with the motion, okay, and this is my mirror 2. So if the light goes from this, okay, and comes back in time 2, t2, so in t2 time, because since the earth is moving with some velocity, this apparatus, this beam splitter will move in t2 time some distance, okay, and that will be c sorry v t2, right? This will move some distance vt2, okay. And what is this distance? We know it, it is L2, right? So what will be the Pythagoras uh, hypotenuse through the Pythagoras theorem? It will be L2 squared plus Vt2 squared by 2, right? Am I correct? And this is same. Okay. Now the light will traverse this much of hypotenuse and this much of distance also. So we need to add up and they are both same. So it will be like this. This squared, or directly write this, L2 squared plus Bt2 by 2 to the whole square. Okay, yeah, fine. So I can, what should I do? Yeah, this can also again be written as, yeah, when you will find this is CT2 actually, because the distance, it is the distance traveled by the light, okay, in time 2. So when you will find the T2 time, it will come out to be 2L2 by C by 1 minus V square by C square. Okay, this is my T1 and this is my T2. Okay, now what will be the optical path difference? Optical path difference will be C into delta T, that is T2 minus T1, and it will be, what will it be? And I can also write this whole T1 as 2L1 C 1 minus V squared by C squared. You can see that. Okay, this is equals to 2L1 by C 1 minus C squared by C squared. Okay, you can write this. Now we apply some binomial expansion. Okay, that is x to the n is equals to 1 plus n alpha x when alpha is very small. Okay, but what is the alpha here? Here the alpha is v by c, and we see that v is the orbital velocity of Earth, and that is roughly equals to like 2 into 10 to the power 4 meter per second. Okay, so when we calculate v by c, it will be like less than -4. Okay, this is dimensionless quantity and it is very small. It's very small. So that's why we can apply this binomial expansion simply and use to simplify our equation. So now our optical path will be 2 L2 by C. Okay, the C is cancelled out, so I can write it neatly now. 2 L2, and what will be this? We can write as like 1 minus C squared to the power 1 minus of 1 half, okay, minus 2L1, 2L1 and 1 minus V squared to the power minus 1. So we can write it as 2L2 1 plus half V squared by C squared minus L1, okay, 1 plus V squared by C squared, right? We can further write it as L2, is something missing. Let me check. No. Yeah, correct. That's fine. So I can write it as L1 minus L1 minus L1, and this is again, okay, leave it as it is. So this is my first equation. Okay, now what we will do, okay, yeah. Now what we will do is now rotate everything. Rotate the apparatus by 90 degree. Okay, and what you will get, you can check. Okay. So again, what you will get here is twice of L2 1 plus. I will tell you why we have rotated but I just need to complete the derivation and we will see in the next class what are the conclusions of it. Okay, this is my rotated frame. Okay, we will and define some delta t. Okay, c delta t as c. Okay, let this be t dash. Okay, now delta t dash minus delta t. What will it be? It will be L2 1 plus v square by c square minus L2 1 plus half c square. Okay, plus plus minus L1 plus this and plus L1 b squared by c squared. I guess I'm going right. Let's see. Okay, what will happen? Now take the L2 common and one will be cancelled out. Okay, this one will be cancelled out and this one will also be cancelled out. V squared minus v squared upon c squared minus v squared by c squared minus of you can take the common from it and then again v squared by c squared and minus of v squared by c squared. Right. Okay. So it is 2 twice of L2. What will it be? Half of v squared. Okay. Let me write it again. L2 half of v squared by c squared. And what will it be? L1 minus of half of v squared by c squared. And this will be L2 by 2 v squared by c squared plus L1 v squared by c squared. You can just write it and cancel the 2 and you will get L1 by L2 v squared by c squared. Okay, this is our result. You see, this phase difference or say the path difference only depends on v. Why v? Because L1 and L2, the the total length is constant of both arms and c is again constant and v is the velocity of earth with respect to ether. Velocity of earth with respect to ether. Okay, so I hope I'm right too. Let me check again. Yes. Yeah. So you can see if I just I'm just about to finish my class. Just hold on. Okay, if the size of the apparatus, okay, suppose L1 plus L2 is 10 meters, okay, and suppose another thing is if the speed with respect to ether, it is like, it is the ratio actually, it is of some order this, and you take the wavelength of light, mm, 500 about, and this is equals to 5 into 10 to the power about minus 7 meters. You see the phase difference, if I calculate the phase difference, C delta C with respect to lambda, I will get it about 0.2, okay, and this is measurable, this is measurable shift while say during the rotation, during the rotation of apparatus, and Michelson Morley apparatus was sensitive up to, it can detect, apparatus could detect, according to Michelson it could detect up to like 0.01, so it was too much sensitive, and you see it's very much larger, so 0.2 is very much larger, so it is obviously detectable thing, okay, it is detectable thing, but the experiment resulted, the results were like during the rotation, during the rotation of apparatus, no shift in interference fringes were detected, or say no phase shift, no no phase shift, or say no motion of earth with respect to ether has ever been observed after multiple repetitions of this experiment. In modern time, the sensitivity is up to like 10 to the power minus 10 sensitivity in modern experiments. So it has never been detected. So this is a great implication in formulating the Einstein's theory of relativity. I will talk more about it, this result, okay. And how did people try to save this ether theory? Because this implied ether actually do not exist. Okay, but there are more explanation of these kind of results of Michelson-Morley experiment, but they will all, I mean, they are all are discarded. Okay, and we will see uh, this will be required for the formulation, or this was adopted by Einstein to formulate his Einstein's, I mean, special theory of relativity. Okay, so this is the Michelson-Morley experiment. I will talk theoretically more about it in next class. Okay, I hope you have written the things, and these were the like experimental graphs of Michelson-Morley experiment, and this was the expected result, but they detected they detected like zero phase difference. Okay, this was they detected zero, observed is zero. Okay, any questions, or you may leave then. Let's end this session. If you have any question, you can ask.
So,
Oh, sorry, I wrote something wrong. Ether actually do not exist. This is, yeah. So any question? Let's end this session then. You may ask in the WhatsApp group. Okay. Let's meet tomorrow then in the morning. Okay. Fine.